Hello, everyone. I think we can start to get started now. I'm Stephen Johnson. I'm the host for today, and I'm happy to introduce Dr. Giuseppe Romano, who's our speaker today. He's a research scientist and a longtime collaborator of mine at the MIT Institute for Solar and Nanotechnologies. He works on materials inverse design with a focus on energy and computing. He's currently the PI of a project funded through the MIT IBM Watson AI Lab on thermal management and microprocessors. And he's also a world leader in the computational modeling and design of nanoscale thermal transport, for which he maintains the open source software OpenBTE. And he also maintains other open source software such as DPV for solar energy. In 2019, he was distinguished visiting scientist at the University of Colorado Boulder. In 2018, he was a visiting scientist at the NASA Jet Propulsion Lab. He first arrived at MIT way back in 2010 as a postdoc in material science and engineering after receiving a PhD in electrical engineering from the University of Rome Tor Vergata, and he became a research scientist at MIT in 2014. So I'm going to hand it over to you, Giuseppe. I'm looking forward to your talk.
Thank you, Stephen, for this warm introduction, and thanks actually Cherise also for organizing this seminar, also for the very nice music selection, I have to say.
Oh, sorry, I forgot to say one thing. If you have questions, there'll be a 15-minute Q&A session at the end of the talk. So please hold your questions until then, but you can type them into the chat or into the Q&A. Or ask them verbally by raising your hand at the end. So sorry about that.
Thank you. All right, so today I'm gonna expand upon our recent efforts on researching differentiable physical solvers that lies at the intersection between physics solvers, automatic differentiation, and flexible software design. There are several applications that can benefit from inverse design. Particular those that are close to my research interests are pertain to thermal energy harvesting. For example, we can harvest our body's heat through the so-called thermoelectric materials, or we can even manage heat in batteries in electrical vehicle, or heat management in microprocessors, or even designing different layers in a PV system. What do these applications, I would say, do this physical solver have in common? Well, or what do they need, right? So the starting point is given by the plethora of popular software for machine learning. We're all aware there are several there, like for example, PyTorch, TensorFlow, or the whole scientific ML ecosystem in Julia and JAX more recently. And they all have one thing in common. They are based on automatic differentiation, which is the cornerstone, I would say, the key ingredients for back propagation, which is also we can call it also reverse mode automatic differentiation. So now I'm going to give a little bit of an introduction to AP. So let's say we want to define a function fx that takes an input x, and it just computes the sign of it, so sin x. Okay. Automatic differentiation not only computes this function, but also the gradient of this function. And in particular, if you're working on, let's say, reverse mode automatic differentiation, the software also computes the derivative of sin x, okay, and multiplies by, in this case, scalar v, which comes from the fact that maybe we are composing different functions. So we use the so-called chain roots. In particular, strictly speaking, what we are working here with is called vector Jacobian products, but I don't want to go too technical here. But the key point here is that the f of x can be really anything that is differentiable, right? So what if we have a linear system that we are inverting? So let's say we have a function that invert a matrix that depends on some parameters rho and multiplies by this vector b. So this is y right now is the solution of a linear system. And why do we care about it? It's because most linear systems are the digital representation of a partial differential equation, and PDEs are, I would say, govern the majority of the physics of physics. Okay, so if we are able to, I would say, hijack this machine learning software for inverse design, then we can rely on automatic differentiation to, let's say, propagate sensitivity from, let's say, a user-defined cost function all the way to the parameters of our system. We're going to go through that very quickly. All right, so in this case, we have, as similar to the case above, the system also computes, for example, the gradient along rho of y, and this is done without user intervention. So this is the key point. All right, so let's make a particular case. So let's have a material that is described by a fictitious density rho. Okay, so let's say we have a picture here. Okay, so rho equal to 1 is equal that corresponds to a solid phase, and rho equal to 0 is a void case. And then we have a solver broadly defined that in this case a thermodynamic solver actually, and then we compute the effective thermal conductivity. So this is what it's called forward model. So we have the material, and then we compute a property of that material. But eventually, ultimately, we are interested in going the other way around. Let's say we want a material that with a prescribed effective thermal conductivity. Here could be also linear elasticity and so on. Yeah. So how do we do that? Well, so let's say we begin with the fictitious density rho, and then we solve the linear system, and then we define a cost function that depends on those parameters rho of the fictitious density rho and on the solution of our linear system. Now, to do inverse design, what we need ultimately is the gradient, as I said, along rho of G. It turns out that if we apply a reverse mode automatic differentiation to a linear system, so basically we are doing an analytical derivative. It turns out that what we have to do is to just solve an additional linear solve. And then we get the sensitivity of the cost function with respect to each pixel of our fictitious density. And I think this is a pretty remarkable result. Imagine that the alternative would be, for example, to include this gradient with finite differences, which of course scales very badly. And so this is not new. The method behind inverse design called a joint method has been applied for decades in mechanics, and also more recently in optics from, for example, the group of Bulovich at Stanford, the group of Professor Johnson here at MIT. But the key innovation brought by this machine learning software, this machine learning packages, that now we can compose user-defined cost functions with arbitrary differentiable cost functions with our physics solver. So we can iterate research, we can do research much quicker without doing the derivative by hands all the time. And also there are also problems that are domain dependent. For example, as we're gonna see through this talk, we're gonna talk about nanoscale heat transport, where inverse design not only needs the adjoint method, but also a material interpolation method that correlates the links the physics of your problems with the fictitious density. All right, so this is just a little example, just a quick example of macroscopic heat transport. So let's say we want to design an orthotropic material that metamaterial in this case, so it's periodic in all directions that conducts heat differently along all those three directions. So here we have, for example, the desired thermal conductivity. Here we define this this cost function. So eventually what we want to do is to minimize G, to find rho, right? The minimize G. Okay. All right. So so this is the evolution of the optimization trajectory. This is just macroscopic heat transfer, just to give an idea. See, here we have the three values. So here we have the thermal conductivity for those three values, the diagonal. So the off-diagonal values are 0. So like that if you want. And here we see the three numbers converting those to the side. But eventually, the material that you're looking here on the left side has the desired effective thermal conductivity. All right. So how do we use it? How do we use this framework for the application that we care about? In this case, thermal energy harvesting. So let me give you a little introduction about thermoelectrics. So thermoelectrics is a field not as known as photovoltaics, but that aims at converting heat directly into electricity by using solid state material. So no flexible part, no noise, and so on. And thermoelectric materials have been used very heavily in spacecraft. For example, the Voyager spacecraft that was sent by NASA a few decades ago. The outer space has been powered by a sort of thermoelectric generator where the heat source is given by a nuclear reaction. In this case, plutonium 238. But also we use thermoelectric materials for converting heat, our body's heat into electricity. The issue that this technology is not as widespread as PV one is that the efficiency is very low, because in a thermoelectric material we want a low thermal conductivity and a high electrical conductivity, and unfortunately a high Seebeck coefficient, which is the temperature response to the voltage response to an application at different temperature, and all those parameters are interrelated. One emerging paradigm is given by nanostructuring that enables to destroy heat transport more effectively than it does with electronic transport. So if we have a characteristic size of a nanomaterial, let's say about 100 nanometers, heat carriers, in this case given by phonons, are destroyed much more than electrical carriers, whose mean free path, for example, is much smaller than the characteristic size. So for example, the mean free path of electrons in highly doped silicon is about 10. The mean free path is just the average distance between two consecutive conditions. So by properly engineering a material, we can suppress heat like effectively by not suppressing heat transport as effectively. So this is what we want. So the figure of merit here is called ZT that eventually goes into the expression of the efficiency. Is the one that we need to boost and maximize. So this as you can imagine, shape here is very important, because the shape really dictates the extent of boundary scattering, the extent of scattering between phonons at the boundaries of our materials. And in fact, the key point here is that at the nanoscales, heat transport does not obey Fourier's law anymore. So there is a dominant, I would say, a significant contribution given by ballistic heat transport that deviates clearly from Fourier's law. So we have to use another model we'll talk about very soon. So here you can see that by just changing the arrangement of pores in silicon, you have a wide range of effects in terms of, this is due to macroscopic effects, for sure, because we have different geometries and different materials, and let's say different porosities here, but also this is due to the different strengths of scattering components and at the boundaries. All right. So here in this design is to go the other way around, is to find the perfect shape or an ideal shape or one of the optimal shapes that can minimize the thermal conductivity while keeping the electrical conductivity above a certain threshold. And just yesterday, a very nice paper came out in Science showing, corroborating the fact that indeed Fourier's law at the nanoscale is violated. Here is the corresponding Fourier's law for electrical currents. Here, the researchers from ETH measure vortices, electrical vortices at the nanoscale in graphene. And of course, vortices is an hydrodynamic effect. It is not covered by Fourier's law. However, it is covered by a more fundamental law that is called that is given by the Boltzmann transport equation. So it turns out that if you work with the Boltzmann transport equation and you compute the moments of it, you can end up with some terms that resemble the viscosity. All right. So if you buy a license from Consol, you're going to get this equation, which is Fourier's law. But over the past, I would say, a decade, I've been involved in developing models and the corresponding software for solving the Boltzmann transport equation. Way more complex. I'm not going to go into the details, but there is one thing I want to say, that the input parameters here are driven by first useful calculations, for example, computed by density functionality. So for the remaining of this talk, I'm gonna solve this equation here, but very simplified form of this equation. We feature this equation in a more complex form that eventually can also compute predict the vortices in graphene. But for the purposes of universal design, we're going to have a very simplified version of this. All right, so here we have some some hydrodynamic signature of heat transport. So we have flux here that follow the so-called possible flux in thin fields. And here finally we are able to predict one vortices in the structure that is similar to those computed by measure from the paper that I just shown. So it means that the model is doing its job in predicting non-Fourier heat signature. All right. And this is the code of OpenBT that implements all these models, and they also be used for predicting material properties, but also for guiding experiments and it's 3 cases. So I'm gonna keep going. So let's see how can inverse design help us here. So in this case, the optimization problem. So here on the left side, we have the baseline, okay, and with an associated electrical conductivity here called Fourier heat transfer, just to say that it's diffusive. And here we have 0.31, these are normalized values. And the goal here is to minimize the thermal conductivity computed by the BT while keeping this threshold above the one of the baseline. So essentially, the question is, we have a material. So the problem that we are trying to solve here is we have a material with a given electrical conductivity and thermal conductivity. How low can you go with the thermal conductivity while keeping the electrical conductivity above a certain threshold? This can be nicely framed in a constrained optimization problem where both the Fourier, the diffusive, and the BT solvers are differentiables in a way that I just shown. So we can use a gradient-based optimization method. All right. So this is the evolution, the evolution, the optimization. And then after, I would say, 100 iterations, we end up with a structure that is made by islands connected by bridges. Okay, and now in a hindsight, you say, okay, this makes sense. Because if you have a bridge, the Fourier transport, the Fourier transport is not effectively is not as affected as the ballistic. So the ratio between the two values goes up. Okay? So this probably something that intuition might have come up with. I mean, I haven't before doing this problem. You know, it's very easy to say after we say, oh, okay, that makes sense, right? But thankfully, thanks to this large scale inverse design problem, we can outsource some of the intuition, I would say, to a computer. All right. So and we fabricate this at the MIT.nano using the focused ion beam. This is our collaboration with Professor Tim Nelson for chemistry and Professor Steve Johnson here at MIT, and also Marco Polandino from now a professor at Northeastern. So essentially here we have a 200 nanometer thick silicon membrane bombarded by ions, and using the feed from MIT.nano. Here, the purpose distance is about 100 nanometers. And so now the next step would be just to evaluate or to measure the thermal conductivity to see if we match the experiment and the prediction. So it turns out that we are close to the so there is a qualitative agreement between experiments and theory here. As you can see, it's a factor of 2. The automatic is there, and the reason we suspected the reason this little discrepancy, this discrepancy is due to some numerical issues. This event is due to the numerical discretization in the reciprocal space that we are trying now to refine better context. Okay, but at least here we get very nice. So the trend is respected, and so we're very excited about this result, and that's why we are moving forward now to the next challenge. The next challenge is the minimum length scale constraint. So as we noticed, yes, we got a four. I didn't say that actually. We have a 4-fold increase in ZT here. However, it expands at a smaller purple size, so feature length. However, it would be desirable to actually have some degree of control of that feature length, and it turns out that this can be nicely framed in a constraint optimization problem where the constraints, the inequality constraints, depend on functions called indicable functions that measure your characteristic length. And this has been applied in mechanics, again in optics, and now we are doing it in nanoscale thermal transfer. So the next challenge was to design inverse design a material with a given manufacturable constraints. In that case, we were able to get 16 nanometers. So, by the way, this work has been so the measurements, the fabrication has been driven by Yang from right that is managing the Valiant, and we have a constant iteration, and it was very nice. It was very nice interaction. And you would say, okay, you can get a manufacturable constraint down to 16 nanometers, then we get this, we would put this number in our solver, and we will come up with a new structure. So 16 nanometers are the thickness now. The membrane is 50, and here can maximize directly this ratio, the electrical conductivity over the thermal conductivity. And we obtain structures like this, and this is indeed 16 nanometers. So the manufacturable constraint is being fully respected. And now we are measuring, and here we obtain an even larger thermal conductivity and boost in ZT. So we're very excited about this, and measurements are ongoing right now. Thermal transport measurement to see if we can have a better match in this case. All right, so yes, so let's talk about the second application case. So I would say the titles are not, the slides are associated to these titles are not uniformly spaced, so don't worry. So cheap is going to be 4 slides, and that's it. All right, so how can we use inverse design and thermal transport to make our microprocessor, our chips get less hot? Okay, so there is a new paradigm emerging recently based on chiplets. So instead of having a monolithic chip, we can just integrate chiplets that are chips that themselves, but they're task optimized. So we have a chiplet for I/O, a chiplet for memory, and so on, and for compute, right? So and now those can come from different manufacturers, and so they have to agree to certain standards in terms of communication. And this has great benefits in terms of modularity, of course, cost efficiency, and so on. And another benefit is that we can move them around now in order to minimize the maximum temperature. So what we want is that when the chip is operating the maximum operational speed, so they get very hot, we want to move them around. Of course, we move them around only once when we do that, when we make the chip, and in order to minimize the maximum temperature. How do we do this? Well, it turns out that we can use what I just described. So let's trace the problem. So let's say the foundry, in this case, we are collaborating with IBM. So let's say the IBM foundry tell us that they have a set of chiplets that are connected through this agency matrix, AIJ. So it's a chip. In this case, chiplet 0 is connected to chiplet 1, and each chiplet has their own its own sites, LX and LY, and very importantly, each chiplet is assigned a power generator, okay, by Joule seeding. So the problem here is to minimize the maximum temperature. Unfortunately, the maximum temperature is not differentiable, but there are many tricks. One of them is using the P norm. So essentially, if you take this, let's say you have the temperature vector, and you elevate each element to a very high number, and then you do the square root of that high number, I would say, okay, or 1 over alpha, okay, to be more precise, you get the maximum, approximately the maximum. Okay, this is differential. This is a concept that I borrowed from another work based on connectivity constraint and so on. All right, so this is differentiable. Another problem that we wanted to, there are other 2 problems here. How do we account for heat dissipation to the substrate while keeping our simulation domain 2D? Like after some simple algebra and consideration, it turns out that we can use an effective heat sink. Here is given by gamma T. Gamma is an extinction coefficient that we can tune, and that depends on the substrate property. In fact, if you move this on the other side, it has a minus sign, so it is an effective sink. And here, okay, so that part is taken into account. And here on the right-hand side, we have a smoothed version of the heat source. So we can just have step-like heat source given by chiplets, but we smooth them out with a 2D half function given by the H. So now the problem is end-to-end differentiable. So we have the degree of freedom, the position of each chiplet. This right-hand side is differentiable. And once we get T, and T with respect to P is even. This is even easier than traditional inverse design because the matrix A now does not even depend on the degree of freedom. We can just invert it once and reduce using it during our optimization. All right, so let's go to the result. By the way, no, another thing, we also have to make sure that the chiplets do not overlap. We use this inequality constraint. I'm not going to go into details, but also we have to ensure that the maximum wire length doesn't exceed that given number. So those are two inequality constraints that we bake in our optimization problem. So let's say this is a design given by intuition where the maximum peak is 166 Kelvin from environmental temperature. If we don't use the wire length constraint, we have this design where actually we got a peak that is 40 degrees smaller. And if we had to compromise a little bit because we want to take into account the maximum wire length constraint, we have this other scenario where we have a little bit other maximum other environment, other chip, sorry, but at least here we are respecting the maximum wire length constraint. So it's kind of we have to play with these numbers. And all right, so all right, so all right, so we have, I'm not going to go into details, but we have some future directions that we'd like to talk about. So one, that direction is given by transformation optics. So essentially, this is a very nice result where let's say you want heat flux not going in certain directions, and you can change the metric of your system. It turns out that once you do that, the functional form of your equation is for optics and thermal transfer remains the same. So we can use the same solver on a different with that space dependent in this case thermal conductivity. So we are now the issue is that though to find the space dependent thermal conductivity, you have to compute a lot of many Jacobians and so on. So we'd like to do it with automatic differentiation. So here this is one type of one line of research, and the second line of research here is that to do topology optimization. So we don't use transformation optics, but we do topology optimization in order to have, in this case, we have a thermal clock. So we want to have external temperature equal to the case where the obstacle were there. This is too much better now. I just wanted to throw it out there. So this is where automatic differentiation can happen in two ways here. Another case, another project that we are working on is to extend inverse design from a pure space modulated material to a case where the materials are modulated in space and time. For example, we can modulate the local thermal conductivity in time just by shining it. And there are many papers coming up there now where we can dynamically tune the thermal conductivity. And what do we care about? Well, there are some recent studies that show that you can really enrich the physics that you want to give to your metamaterial. For example, instead of having a space interface, you can have a time interface. Okay, so it's where you have a material that abruptly changes in time. So the question is natural. So the natural question here is how to extend the inverse design to space and time. So here we have a simple case. Let's say we have a material where we want the steady state temperature here in this part being a certain number. So let's say we are heating this material at the beginning, and we want to have the final temperature be equal to a given number. And here we have the time-dependent knob that we design in order to shrink the channel and to keep the material at a given temperature. Okay, this is a time-dependent problem. And then the last slide. All right, I think we are good time. 1 minute. Is software. All right, so all those applications share the same software infrastructures, which turns out very useful if you want to extend it, for example, to multi-physics problems. So and the software now is called is that Math Inverse. So essentially takes in input manufacturable constraint and it orchestrates different solvers that each of them influenced by the parameter rho. In this case, we keep the material density, and so from this is and from the user point of view, what they have to do is just to write an arbitrary differentiable cost function that depends on the output of those solvers. In this case, for example, we want to minimize the norm of thermal conductivity with respect. Yes, okay, the norm of the difference of thermal conductivity with the desired. So this is the only thing that the user has to do. Okay? And in fact, Math Inverse has been now used for all these applications. that I talked about, and now we're also bringing delta PB to Mattermost to benefit all the routines that the Mattermost is offering. I would like to conclude by saying that essentially here we are using a software like JAX or Scientific ML from Julia, for example, right? So that originally, okay, for example, JAX or PyTorch or TensorFlow, that originally been designed for neural networks, for machine learning, and we are hijacking that, okay, to use it for physics. If you notice, there was no neural network here involved, right? We're just using the automatic differentiation. But you know, as our solvers are differentiable, we can compose them with neural networks to supplement for the lack of knowledge. Let's say we don't have part of we know everything about the system except for a few things, and then we can supplement those few things with a surrogate. So based on neural networks. So this class of solvers then can be composed, it can be in harmony with existing machine learning. All right, thank you very much.
Thank you, Giuseppe. So I think we have a few minutes, 10 minutes now for questions. If people have questions, I don't see any in the chat yet, or the Q&A. You can type them, or you can also click the raise hand button if you want to ask a question verbally. So while people are thinking, let me ask a question. So, you know, the AD frameworks, a lot of them, I mean, a lot of them were designed right now primarily for machine learning applications, people use them for other things. And for doing them for scientific computing, are there places where they fall down, where you have to, you know, supplement them with manually written chain rules? I mean, what's the main weakness of those things when you apply them to these kind of very non-neural network-like computations?
Yeah, this is a very good question. Yes, you have to supplement with custom, in this case, custom vector product for certain functions. For example, in this case, in one case, for example, the whole adjoint method for this here, the whole thing that has to be hard coded in it as we speak. In some cases, you can rely on the infrastructure itself. But for example, in my case, as we speak, I have to come up with my level. For example, if we have a linear system that we want to solve iteratively, right? So it might happen that the first guess that we want in the backward pass is different from the first guess that we want from the forward pass. So we can just use the iterative solver, even if they use the adjoint method underneath. We just can use it directly because we have different first guesses. So in that case, we have to include our own custom vector Jacobi product. Another point I wanted to say is that sometimes we don't even have the problem is self-adjoint, so we don't have to compute the adjoint, but the system does not recognize it. So we have to do, for example, when we were working on nanoscale thermal transport a couple years ago for periodic materials, at some point I realized that the adjoint was just some slight manipulation of the forward model. And so I didn't have to compute it again. But if we just use plain machine learning automatic differentiation framework, the system would not realize that, and we would just waste complete power. So there are a few things that we need to supplement the system with. Yeah.
Are there any other questions? You can raise your hand or type them in and I'll read them out. Okay, so then I think we'll close the webinar now. So I want to mention there is an upcoming talk on June 11th. Is the next talk by Richard Swartwout, who's co-founder and CTO of Active Surfaces, and he's going to be So he's going to give a reflections talk. He was actually the first nano exploration speaker back on March 31st, 2020, when he was a PhD candidate. And now he's going to give a reflections talk talking about his journey as the first speaker in this seminar series as a PhD candidate to now being a CTO of Active Surfaces Incorporated. And that will be the last seminar of this academic year at MIT. So we're done now. So thank you everyone for coming.
Thank you, everyone, and thank you, Steven.